Hi guys, so this lesson is on relative frequency. Now, relative frequency is calculated when an experiment is performed. So how we can work out the relative frequency is we need to get the results of the actual experiment or the event happening. Relative frequency isn't based on what should happen, but what actually does happen. So if we toss a coin 2 or 3 times, right, it should go one heads, one tails, but it's really quite possible to have like um, one heads or two heads or even two tails. And so relative frequency is really about what's actually happening in an experiment. So here below we have an example of relative frequency. Someone has tossed two coins. They've gotten 0 heads 100 times, 1 head 192 times, and 2 heads 108 times. But the thing is, the most important thing is actually working out how many times this experiment happened. How we do that is we just add all these numbers together. 100 plus 192 plus 108 gives us 400. And so now we can actually work out the relative frequency. What we said before was frequency is just the probability of an event is just the frequency divided by how many times it happens, or like how many times there were 0 heads divided by the total number of how many times we flipped the coin. So we are just going to write 100 over 400, which simplifies to 1 over 4. If we do the same thing for the next numbers, 192 over 400, that equals 17 over 25. And if we do the last 108 over 400, that will give us 27 on 100. Okay, so we've got the three relative frequencies there. Now, the next thing we're going to learn about is a simulation. A simulation is a mathematical model that represents a real experiment or a situation. So what we do is we could run tests through computers, we could run tests through coins, we can use cards, but basically if we know the probabilities of what should happen, we can divide them up and then use a simulation to check what could happen. Alright, so here in this example, it asks us to perform a simulation to determine the results of 50 cricket matches. Now, I've done this already, but what I'm going to do is show you how I did this. So the probability of winning a match is 30%, drawing is 50%, and losing is 20%. So really, we have three outcomes. We can win, we can draw, or we could lose. Now, in this hand of cards, you'll notice I have 10 cards. 2, 4, 6, 8, 10. Each of them with a different number going from ace or 1 all the way to 10. Now, if I think about this, it doesn't matter what number I assign. I'm just going to assign winning as 1, 2, and 3, drawing as 4, 5, 6, 7, 8, and losing as 9 and 10. Now, when we have 10 cards, if we have 3 of them, that is 30% like so. If we separate out 5 of them, that's the same as 50%, and the remaining 2 is 20%. And what I would do is I would just shuffle the cards, okay, making sure I have a chance of picking any of them, and then just flipping a card like that. Alright, now what I've already done is I've done a table. So what I've just got is the scores, okay, and because I don't have enough space, I've split them over 2 columns. And then what I've done is the frequency, or how many times it's happened. Alright, so what I've done is I've shuffled them, and I had drawn an ace 3 times. And then I've drawn a 2 5 times. And the rest of the data is like so. Okay, so I had shuffled them, and then every time I flipped the number, I would add it to a tally. Alright, you can see that tally on the previous example that I'd done. Alright, and then we worked out that in total, the times we had won was 12 times. the times we had drawn was 31 times, and the times we had lost was 7 times. And that's our relative frequency just from our simulation of drawing a card from a deck. Okay? Now the next thing we're going to work on is another frequency table. Right? So this question talks about a frequency table showing the outcomes of an experiment. So how can we work out the relative frequencies? Like we remember last time, we're missing a really important number, and that's the total, okay? By adding all our frequencies together. And then what we can do is just do 8 over 86. That simplifies into 2 on 17. Use our calculator and that SD button to really speed things up in simplifying fractions. 20 over 28 is the same as 5 on 17. 28 on 68 is the same as, I think, 7 on 17. And then 12 on 28 is the same as 3 on 17. Okay, and so that's how we get our relative frequency really quickly from using our calculator and then the SD button. Whoops, 12 on 68, I wrote the wrong number here. And that will fix that fraction for us. Okay, now this next example is also telling us to use a simulation again. Alright, now what I'm going to do is I'm going to show you something different. It tells us to do 148 trials. Let's not do that. Let's do 10 and then 20 trials. But before we do that, we need to assign each candidate a result from our simulation. Now what you have on your calculator here is a random button. Alright, that RAN button there. Okay, and that's in yellow. So we want to push shift and then that dot, and then we end up with this random button. Now, what that does is that will assign you a random number between 0 and 1. Okay, so for example, if we keep pushing that, we'll notice 0.162, 0.161. Sometimes there is a 2-digit number. We got pretty lucky there. And that is just the same as 0.740. Okay, so it's still a 3-digit number. The last one's just a 0, and your calculator's smart enough to actually go, oh, I don't need to put that 0 in there. So if you're a little confused why sometimes we end up with 2-digit numbers, sometimes we even have a 1-digit number, all right, that's the reason why. So what we are talking about is 4 candidates. And what we need to do is split the numbers from 0 to 1 into 4 different categories, A, B, C, D. Now there's many ways you can do that, but the easiest for me would just be going, okay, for any of the numbers from 0 to 250, right, or 0.250, that will be my candidate A. And then on the second side, I would go, okay, so from 0.251 to 0.500, that will be my candidate B. Any of the numbers that land between 0.501 and 0.750 should be candidate C. And candidate D would be 0.751 all the way to the number 1. And that means now, if I start pushing buttons, 0.179, boom, candidate A. 0.363, candidate B. 0.954, candidate D. And I can use this method to actually come up with a few trials and our relative frequency of our simulation. Okay, so now we've got a strategy. Let's actually run some tests together and start to draw our graph. So 0.92, that's candidate D. Let's just 0.43, that's candidate B. 0.89, candidate D. 0.81, candidate D as well. 0.3, candidate B. 0.034, candidate A. All right, and I'm gonna do 1, 4, 5, 6, 7, 8, 2 more. Candidate D is a strong favorite right now. And this is after 10 simulations. Okay, so let's write the numbers down first. 1, 3, and 6. We'll notice that these all add up to 10, all right, and that's great. So let's keep going. Let's do another 10, okay? 0.05, 0.92, 0.93, 0.642. Okay, finally C is on the board. 0.758, oh, so close. 0.366, 0.6, 0.04. Okay, so 2, 4, 6, 8, 10, 12, 18. Let's do 2 more. All right. Now, if we compare our candidate, well, when we tested 10 and now when we've tested 20, can you see that this is starting to even out a little bit more? All right, C is starting to get a few more votes. And as we saw before, each candidate is equally likely to win. So theoretically, all these probabilities are actually quite close together. Now, we're not going to have to really deal with this situation a lot now, but something you should know is that the more trials we do, the more our experimental probability, what we're doing in the simulation, should actually match up with our theoretical probability, which is the fact that each of these candidates should have an equal chance to win. All right, so if we tested 148, all right, then we should get pretty close to each of these candidates winning 37 times each, because 148 divided by 4 is 37. Now, this doesn't always happen. If you actually went yourself and did this trial 148 times, even if I kept going, you probably go, oh, okay, like D was quite common, right? But yeah, like that's the kind of example we're thinking about when we deal with probabilities here, all right? So in terms of answering the question, have we kind of done this? All right, we've completed 20 trials. Have we used a frequency table to record? Yep. Relative frequency of each outcome. We just needed to divide all of these by 10 or these by 20. And then the probability of candidate A would have depended on which probability we used. All right, so that's question 8. We're going to skip question 14 just because it uses a lot of Excel stuff. But let's finish on question 16 here. Now, when you look at this, you instantly know you are missing your total. All right? Now, that's actually question C. And what I would recommend is actually working these questions and going backwards, solving C and then B and then A. Okay? So, how can we work out the total of the scores? What we know is the frequency, right, is made up, or the relative frequency is made up of the frequency divided by the total number of scores. And so right now we know that the relative frequency is 0.25. We know that our frequency is 5. So 5 divided by something gives us our 0.25. If we were to solve this as an equation, you'd be like, hang on, if I times x by both sides, and then I have 0.25x equals 5, and then I divide by 0.25 from both sides, our x equals to 5 divided by 0.25, which equals to 20, and therefore the total number of scores would be 20. Okay? Now, what we also know is the frequency divided by the total of scores is our relative frequency. So now we have the frequency here, we have the total scores there. So to do part B, 5 over 20 is 0.25. And you'll notice that if we have the same frequency, then we should have the same relative frequency as well. And that's why we know that this answer is correct. The last thing we need to do is to work out our last missing frequency. Now, if you have this formula here, girls, it's important to know that the relative frequency, 0.2, is equal to the frequency, which we don't know, divided by 20. And so now, if I go, hang on, if I want to solve this equation, I need to do the opposite of a divide, and times by 20 on both sides, and then that equals to 4. So the missing value of x is 4.